Recording. Okay, well, so we're starting actually towards the end of the first lecture with the recording. First hour of the lecture almost, well, half an hour. So we've skipped some points which I'll talk later to the video. But now we're essentially going forward from yesterday. So we had a brief introduction to different differentiation rules and the central difference. Am I actually sharing my screen? No. Let's share the screen as well. There we go. So we do have just differentiation rules and had a little look at the symmetrical difference quotient, which is great for most numerical uses, but doesn't work exactly the same time in some of the exceptional cases. Then we do have some rules, so you don't always need to take the limit. If you want to find out the derivative, we have some, yeah.
The slope is
Slope isn't, okay, so slope isn't in the Moodle. Okay, I'll add it.
Also, I'm pretty sure versus y variations.
Okay, I'll need to check that as well. So apparently there are a few slides missing. I'll need to re-upload the slides from my computer. So I was taking the ready PDF from last year, and apparently I've made edits. Do you need a break? No one at least admits, so let's go on. So basics, if you have a power, then you reduce the power by 1 and take the power as a multiplier of the derivative. Then some power of the function works exactly the same way. So there we have the power of the variable and then separately power of the function. And the difference here is that we're using essentially the chain rule in the right-hand case, where over here we still need to differentiate the function itself. Then if we have the natural logarithm, so this is, I assume you know what logarithms are. That's the base e logarithm of the absolute value of x. Then we go to the 1 over x, and for generic logarithms, then we get the formula right. E to the power of x differentiate as e to the power of x, and a to the power of x gets the logarithm in it. This is essentially from the definition of the logarithm, and because we're talking natural logarithms, there a needs to be greater than 0. And then same for some trigonometric rules. There's a lot more of these which you can find from tables. And if you need to check something, or if I need to differentiate formulas myself, I rather commonly go to Wolfram Alpha. How many of you is familiar with Wolfram Alpha? Okay, 1, 2. Okay, so Wolfram Alpha is essentially a, what do they market themselves? Knowledge engine. So it does stuff with known statistics and things like that, but it can also do things like derivation. It's usually rather slow. Let's see if it understands what I'm asking it. Yeah, okay. D over dx, x squared plus 2 is 2x. So it does have a homework mode, but you're not supposed to copy paste your homework from this alone. But it helps you check the answers if you're doing simple differentials. And it can also do, it occasionally gets confused if you're doing really complex stuff, but it can also integrate. So we can do things like integrate that x equals from 0 to 10, and it should understand that. So we get the definite integral of that. Relatively useful, but also try to practice the following approach we're going to go through now. So I think first I should have gotten, I think I promised someone that I need to put a picture of Julius Caesar here. So one simple way of starting engineering problem solving is this divide and conquer method. So in this kind of a problem, which is relatively simple, we identify the function parts. So we divide that into parts where we get the fx is 3x squared, gx is now minus 5x, and hx is minus 7. And then we can also, if we really want to go to elementary functions, then we can take the multiplier 3 out. So then f2x is just x squared. And same on the second case, we can take the minus 5 out, use the elementary derivatives, apply differentiation rules, and then we get our answer by substituting back. So that for this kind of simple cases, this feels really silly. But then on more complex cases, it really helps that you can do it piece by piece and don't need to do a really complex formula at once. Of course, occasionally, if you start working on the complex formula, you can see that some things cancel out. So this is not an absolute rule that you should always do it like this, but in most cases, it helps a lot. Okay, if we're doing some examples, now, yeah, I've unplugged that computer from the network because I'd really want to be able to, well, on the whole, I can show this. No, I cannot. Wait, that screen stays on. So now on the whole, I can show these. These should be found on the slide set as well for those who are following remotely. So I can show you the camera again. And no, it doesn't show up. Yes, it does when I just stopped sharing that. And yeah, so we can get those on the screen here at the lecture hall. So these are something you should be able to do by yourself as well. But the first example is 3x squared minus 5x minus 7. Okay, we can immediately, if you want to differentiate that, we know that t is gonna go to 0. And we can ignore that safely. And then we end up with 3 dx squared minus 5 dx. Okay, x to the power of 1 equals to x to the power of 0, which is 1. So this ends up being 1. X to the power of 2, that's 2x by the differentiation rule, and then we substitute back, so we get 3 times 2x minus 5 times 1. So the differential derivative is 6x minus 5. I occasionally may get confused with the Finnish and English terms because the this process in general in English is called differentiation, and in Finnish we call it derivointi. And the end result is derivate and derivata. So it's has to say in both languages. The next one, okay, we're having x to the power of half. How does that work? Any ideas? Yeah, sure. It works exactly the same way. Power minus 1. One important thing is that it might be a square root, so the square root works slightly differently by definition, but this works exactly the same. Then how would you do minus 5 over x? So in that example, we have 4x to the power of half. Well, okay, we can differentiate that dx. So that's 4 times x to the power of half. This is done exactly according to the rule. So this ends up being 4 times multipliers of the front. So 1/2 x minus 1/2. Highly likely. It has crashed a lot in the last few weeks. All right, well, that's not good. Oh, one important thing that is, right now still, I haven't fixed it on Moodle, assuming Moodle works. One of the exercise rooms does have 20 places on the chair, and it says on the room that there's room for 20. But I went there and counted the seats. So unless someone wants a standing seat, there's only 16 seats in that room. So that 20-person exercise actually has room only for 16 people if you want to sit. So next part is this is really connected. So we have this minus 5x. Now how would we differentiate that? Okay, minus 5 we can take to the front. Minus 5, and we get dx 1 over x. And what is this 1 over x?
Would we just take x on top and do x to the power of -1?
Yes, exactly. Thanks.
No problem.
Yeah, that's 5 dx x to the power of -1. And same here, so this could be x to the power of 1/2 going downstairs in the previous example. Okay. It's going to be wonky probably for a few weeks still until they work things out. It has been worse because when I was still a student for the last few years, we swapped the provider for where the university web pages were hosted. And back then, we still had these on-paper study guides, which were no longer on paper, but on PDFs. And all the web pages related to the university crashed, and no one could access them. I do remember that I had, when they were briefly up, I downloaded the study guide and put it on my home page, and just an emergency, if you cannot access the university homepage, then try here, point it to my home pages. And if you don't know what a home page is, it's kind of like a kind of Facebook profile you need to maintain yourself. So that level of information sharing back then. Same thing, so the third example is simply looking at, okay, now we need to know with regards to what we're differentiating. So if we're doing this s to the power 5 minus s to the power 3 over 15, if we're differentiating with regards to x, and that's a constant, it goes to 0. But if we're differentiating with regard to s, So we can differentiate that as normal. We could take the common term 1 over minus 15 and then differentiate separately s to the power 5 minus s to the power 3 and then substitute that, or maybe take shortcut either. Again, we have a cubic roots. Cubic roots work exactly the same as the square root. So a cubic root is cubic root of x is same as the x to the power of 1/3. So we can reduce that to fractional powers. So that's the really quick rehearsal of how to differentiate. I guess most of you spent like at least one period of high school to go through these. Oh, and we got the final one. Yeah, well, now for the final example, we're going to get fractions from the square root of x. We can either use a chain rule to differentiate those separately, or then we can multiply that back in with the formula here and then separate that into elementary functions and differentiate those. So it depends on which approach you want to take. Unknown functions. We can also differentiate unknown functions. This appears, we can apply the product and quotient rules exactly as was. And now, as long as we follow the rules, and we do have somehow, for example, measured, oh, this is not shared. Let's share the screen so all the people can see this. Okay, there we go. So now we could use the same rules we had before, and we had more of the screen, so now we have those formulas there. So we could do the differentiations as is, exactly by the rules, and then after applying the rules, we can substitute the values for x, fx, and maybe the differential of x, and still get the results. So this is something that is often forgotten, that you can perfectly well define a function as a table of values. This will happen if you're doing any kind of measurements. For example, if you measure speed and acceleration, you do have, okay, location, speed, and acceleration would be x, maybe fx, and the differentiation of the derivative of x. So that in that kind of example, you might have the measurements there, but you don't exactly know what the exact function is. So in those cases, you can still do derivative work if you need to find, well, if you already know acceleration, maybe you were interested on jerk. How many of you have heard the term of jerk in this context? If speed is the derivative of location, acceleration is the derivative of speed, jerk is the derivative of acceleration. So how fast some machine can accelerate, for example, is called jerk, and it's written in the same way as someone would be saying, hey, you're a jerk. And actually that was all for T's. Then we're going slightly, this wasn't in the last year's slides, so hopefully it's on Moodle. If not, then I'll upload it ASAP. Actually, this probably was. So then the integral can be taught as an antiderivative. So if we know how something changes, we could try to figure out what it is. But we may also consider it as a volume under the curve. Of course, if we're having curve that's below the axis, then we're having oddity because we're then having somehow negative actual area or volume, depending on if it's a 3D or 2D. So that kind of breaks down. So we'll need to just remember that. And one way to define this is that we can take the area by parts. So, for example, divide by parts where it crosses the axis, the function crosses the axis, or then even smaller parts, depending on what we're actually doing here. So the Riemann integral, how you usually say what an integral is, then the integral is taking the average value of function, which here is marked with fb, and multiply it by the interval length. And then, if we want to know what the integral is at the specific spot, then when this interval length, so length of a step, goes to 0, then the interval value of definite integral approaches the integral value of the indefinite integral, which is pointwise. And this kind of value where fb is the mean value of function within that interval exists. We know that because last time we had talked about an intermediate value theorem, that if it's a continuous function on that interval, we must have all the values in between. That value must also exist on the interval. And the definite integral, usually if we just pick one value as an estimate, we are getting some error. So for this squiggly line on top of the area means that it's an estimate. And then when we're taking more of these estimates and sum them up together, we should be able to get an estimate. Is missing. Oh yeah, the h is swapping from different sides. So then when the h goes to 0 and we get more and more slices, we should get a more accurate estimation by this kind of a numerical calculation as well. So the end result in theory is that we're having infinite amount of slices that are with 0, but that may be something that's indeed slightly hard to comprehend. So when we're having non-zero widths of the individual intervals, we're doing numerical approximations. In derivative, if we cannot count, if we have just some system that tells, for example, what value the model is, we might, for example, have a simulator for a system which tells the outputs at certain parameters. We don't know exactly what's the function in there. We can still do derivatives. So we're looking at the numerical side now. Then we can compute different slopes and, for example, average or estimate that if our h here, the step is small enough, then it's close enough for our all practical purposes. So this is the engineering side of things. So there's a common joke of prime numbers and scientists of different fields, and a mathematician, a physicist, and an engineer are asked to estimate what is, if it's true that all odd numbers are primes, prime alkuluku in Finnish. So the mathematician starts, okay, 1 is a prime, 3 is a prime, 5 is a prime, 7 is a prime, but 9 isn't a prime, so okay, this is proven. The physicist goes, 1 is a prime, 3 is a prime, 5 is a prime, 7 is a prime, 9 is a measurement error, 11 is a prime, and then the engineer could go that 1 is a prime, so on, and 9 is a estimation error. So it's estimately a prime. So occasionally you can fudge it if you're still getting good enough numbers out of it. The really hard part is to know when you can just trust on the estimate and when you need to check your results. If you're taking numerical results, it's really good thing to substitute them back into original formulas and check if those still hold. Also, yeah, we can do derivatives on a time series as well. So essentially, we can estimate So if we have a string of measurements, then by difference of those, so we calculate the slopes between each of the measurements. That's one way to estimate the derivative. Or then maybe we could fit sections of a polynomial there or something like that. But that's something that should be encountered more on. It used to be on something like second or third year stuff, but it's probably more happening now on your master's studies. We were talking already about symmetric difference quotient. This is how we arrived to symmetric difference quotient. So we take the difference quotient on both sides, add them up, and take the average of those, and we end up with the symmetrical difference quotient formula. And this way, we actually can take the proper limit on this formula as well, but it just doesn't happen to have any difference which way you take the proper limit, because we have a plus h and minus h. So looking at different sides is just mirrored cases. Numerical integration, okay. We pick some value. There will be error if it's not exactly on the integral side. If it's not exactly the true mean value, there will be error. The more unsmooth, to use this term, smooth the function is, and the longer the estimation interval, then we are going to have more error. One example of this in terms of if we had a jar here and we want to know how much the volume of the jar is, we could have that and put objects into it. We know how large those objects are and how many we can put in the jar. And by calculating those, then we estimate how much stuff fits in the jar. So when we have larger objects, we cannot fit as smoothly them into the jar. We're going to have error. But smaller the items, then we have a better estimate of how large the jar is. In numerical computation, you can just typically you can go ultimately small. So in a physical example, we can pour water into it and then measure how much water there was, and we get a pretty good estimate how large it is. But with computers, eventually, when you start adding small enough numbers, we go below the counting accuracy of the computer, we start rounding. So if we have a really big number, which the computer cannot represent all the decimals of it, we get add a really small number, it rounds as if we added zeros to the number. So that's something you need to be careful of when you're using really not large numbers, which you add to really small numbers on computers. And yeah, discrete time signals, pretty much any kind of measurement you may have, you are getting just some points of the function, usually with some measurement error as well. So the simple way is that we take the rectangular integral. So we just assume that the function stays constant between measurement points, and then just count the areas of these rectangles. There's going to be an example in a few slides in. Or then we might fit trapezoids, puolisuunnikas. So we fit straight lines and then calculate that there's a triangle and there's this rectangular area between these points and calculate that. In both cases, typically there's a window, so not using just between 2 points, but we are using a longer point and maybe some kind of a smart things there. So rectangle rules to fill the underside of the function with boxes and just sum the area of those boxes. So the formula works like that. So now do note that this is the beginning point formula. So we're using FA, which is the starting point. So it probably isn't the average there, but if the interval is short enough, we're getting close enough answers. And we get some formula. Midpoint rule might be better for many users, but now we need to calculate what's the midpoint. So if we have already know values at the end points of the intervals, then this causes extra calculations. And what the midpoint rule looks like. So in cases where the function curves down, we're getting some extra area there when the function curves up, we're not having enough area, and then on those slopes, we're getting pretty close to the true estimate of the function. Trapezoid rule, this is formula, so it's the same thing what we're using trapezoids. So assume what if we fit straight line segments on the function and then calculate the trapezoid area. So we call that kind of a box where at least one of the, and at most two opposite sides are slanted. That's called a trapezoid. Puolisuunnikas. So box with a triangle at top base, but in this case, because we know that the axis is always straight. Hopefully, otherwise we're getting to pretty complex geometries. And yet we're also, in some cases, it's how many of you are familiar or heard about Simpson's rule? Okay, a few people. So Simpson's rule is essentially the same thing. So if the rectangle rule is that we estimate what if the function is constant, trapezoid rule is what if the function is a straight line, and Simpson's rule is what if the function is estimated as a parabola. And that's all for today, folks. We went yesterday a bit too long, and tomorrow I'm trying to have a look at few practical examples where we have actually used these things. Probably not going until 6 o'clock tomorrow. I usually don't see the point, especially when for some people we start to have exercises which are just before the Thursday lecture. So if someone has 4 hours of maths in row from 2 to 6, that's maybe getting a bit much. I'll try to have, I will have a few exercises of these, maybe on the non-graded ones. These should be easy. And I'll try to get over the weekend the next week's exercises and a few things. Let's see if Moodle works, because I should have stuff for you on Moodle. So I'll need to send email of this as well. But there are 2 questions. How long are you working remotely? So if you are currently not here, would you kindly tell me how many weeks you are still away, so I can know what kind of things I need to prepare. And then select your exercise group. And this is still having an error because one of these, okay, I'll still need to add actually a non-zero limit to the remote exercises, sorry about that. And then one of these is also having a limit of 20 people when it should have a limit of 16 people. So I'll need to correct.
What times
Time edit shows the exercises. So there's a link here, timetable available in time edit, which should show you. So next week check out those times. So one exercise is 3 o'clock on Wednesday. One exercise is 2 o'clock on Thursday. And for remote students, not sure if I'm gonna, well, I could try streaming one of those, but also I'm available by email, and if I'm free, I have one more exercise that's not on this course, which is on Tuesday evening. But in general, if my Skype for Business or Teams shows that I'm free, feel free to drop me a message that, hey, do you have time? And if I have, then you can take me a video call or something, and we can look through your exercises that way as well.
So if my remote is 2 weeks long,
Yeah.
do I go into remote or do I choose another exercise group?
You should be able to actually switch, but if you want to reserve a seat, then there should be enough seats for everyone. So on this course, we're not having the trouble that not everyone fits into the rooms. Then do pick the exercise that fits you better.
Okay. And on time edit, it will tell you which is group 1 and which is group 2?
Yes, group 1 is, okay, it says harjoitusryhmä, oh great, this is only in Finnish. Harjoitusryhmä 1 means exercise group 1, so it's on
Okay.
Wednesday, and harjoitusryhmä 2 is exercise group 2.
All right, thank you.
And hopefully these don't change. Occasionally these swap around, but let's keep it so that the Wednesday one is 1 and Thursday one is 2.
Okay.
These do actually change when we go to second period, and then we're having one exercise group on 4 o'clock on Tuesday, which is not really my favorite. Okay, our lectures do also. Oh, that's gonna hurt. We're gonna have Wednesday morning from 8 to noon as lectures. Okay, I might want to ask the timetable team if we can change some of those lectures, because those look painful for the second period. Also, I'm kind of promised that I need to be elsewhere on Monday evenings, so that's not really good for me, but I'll check that. But trouble is, I don't know any of your timetables otherwise. But I'll try to ask.
Okay.
But yeah, do reserve a spot on the exercises, and it may be that we have a separate registration for the second period. But the first concern is that if you can get on the exercise on the first period. And
Okay, thank you.
yeah, attending is not mandatory, but it typically is the best part that you can do together. Now, of course, if you want to do together, you don't need to do that on the exercise halls. You can also work with each other. On the exercise halls, we need to use masks. Okay, we have no way of enforcing that when you're working by yourselves, but kind of be careful, okay?
Okay.
Any other questions? There was one question that was a good one on yesterday. Do you have to return the paperwork? There will be an electronic returning tool, so if you want to do them with some electronic tool, you don't need to write them on pen and paper and then take a picture. You can just return the PDF or something like that.
All right.
As long as I can make it out what you've been doing.
Okay. Okay, thank you.
Welcome. And usual ethics, I'm not going to enforce that, but if you're working in a group, kindly mention that, hey, I work with this and this, because later on, that's actually enforced that if you're caught using exactly the same work as someone else, which actually is really harder to check on the digital parts. Yeah, do ask. Next week, yes, not on this week. Yeah, that's so that we have time to select the exercise group and have a look on those. So otherwise it will be relatively quick, especially now when we cannot take more than the specified number for exercise groups. So otherwise it would be, so we cannot take more than, well, okay, one of the rooms technically we can take 20, but there's still only 16 seats, so I'd rather not have you sit on tables or something like that. Last year we had one big course where we simply couldn't fit on the room, so we had people just sitting around the room, but that's not a really good one. Yeah, do ask.
How does the demo registration?
Usually in no real way. So I'm trying to put the demos in the middle of the normal lectures as well. Last year we had such a way that we had occasionally invited. The plan was that we invite maybe some guest lecturers to show how it's what we really use for those. But it's in the lecture plan that we have some demos and some normal lectures. The plan is to mix them together. So I should not be doing just the basic theory and then all the application in one, but I'll try to mix it up that we go through a little piece of theory and then look at the applications, then continue with theory, look at the applications, so they should be mixed up. Any other questions? Also, my email is available. I read it relatively religiously. One important thing, I do get a ton of email, So if you click that link, it automatically adds on your email this course identifier. So remember to keep that string there on your email. So when I search for course-related email on my inbox, I will find your emails and hopefully filter out the spam. You don't need to use the link. This is also fine, but just engineering maths is not fine because it's going to match with everything that has the word engineering and everything that has the word maths in it. So I'm going to find also a lot of spam. So if you use the course code, then I'll be able to filter out only the messages that are related to this course. You can then add something there that, hey, when do the exercise start? So it's also nice to have something on the topic, so I can more easily find discussion related to one topic. My office is still 6319B. So if you want to, if I'm there, so essentially if the lights are on, then come knock and I'll usually answer. It's a bit too crowded, so we're not supposed to have many people there. But the pizza tables are next to it, so we can then try to see if they're table free and go discuss there.
So are you in the
It's on the ground level. So six building, third floor.
Yeah, you just said 6
6319. I mixed up the numbers at one point. Yeah, six building actually doesn't have floor 1. It starts on floor 2. Yeah, it's also at the levels are the same. So only the first building and I think the third building do have floor 1. First building does also have floor K, Kellari, so it does have a basement. And I think there is some individual rooms where there's a floor K2, the second underground level. But it is odd on many places. Highest places, there's a laboratory on the roof of the 6th building, which would be 8th floor. But I don't think it's ever been used. It was supposed to mount antennas so we could research on radios, but then the researcher would have done tests that moved to a different university, and there's just an empty room. Oh, what do I know? Maybe it's a villain layer or something like that. Okay, any other questions? Okay, I guess then that's it. We went a bit over time yesterday. We are a bit early today. So on the average, we're doing good. And now I need to remember to